Hi Year 11. So, retrieval roulette, get your books out, pause, get these answered for me please. Okay, so here are the answers. That question 3 there, the nuclear structure of the atom. Remember, it is the nucleus in the centre, and inside the nucleus you've got protons and neutrons, and then orbiting around the outside you have got electrons. I think the rest of them there are okay the way they are. So if you get those marked and corrected, thank you very much. Right, so last lesson we were doing these questions on page 189 and 190. So if you open up your folder at those questions, we're going to go through these and then you can mark and correct your work properly. Okay, so question 5, this diagram here, the blades of a helicopter exert an upward force of 25,000 newtons. There it is there. The mass of the helicopter is 2,000 kilograms. For part A, we had to calculate the weight of the helicopter. So for that, we would use W equals mg. The mass was 2,000. Gravity is 10. So that means our weight is 20,000 newtons. So what I would do now is mark that on my diagram. So the weight is 20,000 newtons acting down the way. For part B, let's see, calculate the acceleration of the helicopter. Well, if we look at the forces that are acting on this, we've got 25,000 newtons acting up the way and 20,000 acting down the way. So the resultant force is going to be acting up the way. So we're going to use F equals ma. Now, when people went wrong in this question, this part here was the most common place that they went wrong. So the resultant force on this is this 25,000 newtons acting up the way. Take away the 20,000 newtons going down the way. So 25,000 take away 20,000 equals mass, which was 2,000, multiplied by the acceleration. So 25,000 take away 20,000 gives us 5,000 equals 2,000a. If I divide both sides by 2,000, I get 2.5. So acceleration 2.5 meters per second squared. So that's the two answers there. Okay, so the most common mistakes that I saw were people either just putting in the 25,000 here for F because you forgot about this wee weight force, or a few people subtracted the mass from the 25,000 as opposed to the weight. So just be super careful with that. So number 6, I had given you some wee hints at last lesson. Let's read through it again now. So a forward thrust of 300 newtons exerted by a speedboat engine enables the speedboat to go through the water at a constant speed. So for this scenario here, this speedboat is pushing forward with 300 newtons. It's going at a steady speed. That tells us, right, the forces have to be balanced. So there must be resistive forces here of 300 newtons. Okay. It tells us the speedboat has a mass of 500 kilograms. Calculate the thrust required to accelerate at 2 meters per second squared. So this is my second scenario here. Now it's accelerating at 2 meters per second squared. We have to figure out the thrust, but we can use this earlier information to tell us that the resistive forces acting here are 300 newtons. So for this diagram here, I'm going to be using F equals ma. Now, my resultant force, and the F in F equals ma is the resultant force, is going to be the thrust take away the 300 newtons. Because it's accelerating, it's going to be going in the direction of the thrust. So that must mean that the thrust is the bigger of the two forces. So thrust minus 300 equals mass. Now, what was it? I didn't make my list of information. Now I'm having to go hooking for it. The mass is 500 and the acceleration is 2. So the thrust minus 300 gives me 1,000. So to get the thrust on its own, I have to add 300 to both sides of this equation. So that gives me 1,300 newtons. Now, the most common mistake that I saw there was people getting this 1,000, but then they took away the 300 as opposed to adding it on. So hopefully you can see why it ends up getting added on. And this is my preferred method for making sure that I don't make that mistake, that I substitute it in to my F equals ma the way it is in the diagram, as opposed to trying to do it in two separate steps. Right, let's look at 7. A car and driver are travelling at 24 meters per second. So that's our initial velocity. And the driver decides to brake, bringing the car to rest. So the final velocity v is 0 in 8 seconds. The mass of the car and driver is 1,200 kilograms. For part A, we have to calculate the deceleration of the car. Well, if I look over at this list of information that I've made here, I have all the information needed to do that. So I'm going to use my acceleration equation. So A equals v minus u over t. Final velocity is 0. Initial velocity is 24, divided by the time taken, which was 8. So that's going to get me minus 3 meters per second squared. So it's an acceleration of minus 3, which means it's a deceleration of 3. Okay. Part B, calculate the size of the unbalanced force which brings the car to rest. So that's going to be the F from F equals ma. The unbalanced force is just the resultant force. So the mass we have over here, 1,200. Acceleration. Now, a couple of people asked me about this. I would just put my acceleration in here as 3, okay? Some people put in minus 3, and let me just finish this off, sorry. Right, so that gets me 3,600 newtons. If you put in minus 3, that's going to give you minus 3,600 newtons. That's fine. That minus sign just shows you that the force is acting in the opposite direction than the object is going in. So say I am moving over to the right, and because this question is about something slowing down, so say this is the car here and it's moving to the right, well, the force is pushing it this way because it's going here, and the force is pushing it this way to bring it to a stop. So the minus, if you put minus there, that just shows you it's going in the opposite direction. Mark it right, okay? Right, let's look at it. So a cyclist and her bicycle have a combined mass of 60 kilograms. When she cycles with a forward force of 120 newtons, she moves at a steady speed. Okay. However, when she cycles with a forward force of more than 120 newtons, she accelerates. So for part A, explain in terms of forces why the girl moves at a steady speed when the force is 120. So whenever she's pushing with 120 newtons, we are told she goes at a steady speed. That means the forces have to be balanced, so the resistive forces must be 120 newtons as well. So the forces are balanced. Resistive forces must be 120 newtons. Part B, calculate her acceleration when the forward force is 300 newtons. So now she's pushing forwards with 300 newtons, but we know these resistive forces of 120 newtons are still there, right? So we're going to use F equals ma. The resultant force is going to be the resultant of these two. So it's going to be 300 take away 120 equals mass. Haven't made my list again. Let me see, there's the mass there, 60. And we have to get her acceleration, so that's our unknown. Now, the most common place that I saw people going wrong here was just putting in the 300. So just be careful. Remember, anytime they give you all this loads of information, it is going to be a situation like this. They've told you this so that you recognise that the resistive forces are 120. It's really, really sneaky. So anyway, 300 take away 120 gives me 180 equals 60a. If I divide both sides by 60, I'm going to get my acceleration to be 3 meters per second squared. Okay, so that's that one. Over the page to question 9. A car's brakes are applied and the vehicle's velocity changes from 50 to 0. So u is 50, v is 0, and it takes 5 seconds. Calculate the acceleration of the car. So this is just like that other one actually. So a equals v minus u over t. V is 0, u is 50, divided by the time, which was 5. So that gets minus 10 meters per second squared. Now at this stage I'm having a wee quick glance up. Yeah, it did ask for acceleration, so the acceleration is a minus, so just leave your answer like that. If it had asked for deceleration, then I would put positive 10 in there. Now B, the resultant force causing this acceleration is that many newtons. Calculate the mass of the car. So it's going to be F equals ma. So our F is 18,000. Mass is what we're looking for. And acceleration technically is minus 10. But remember, we don't need to worry about that minus there. The minus is just showing us the direction. So I'm just going to put 10 in there. Divide both sides by 10 and I get 1,800 kilograms. Okay. Right, question 10. A car of mass 1,000 kilograms is travelling at 20 meters per second. So U is 20 when it collides with a wall. The front of the car collapses in 0.1, I think I used there. That's horrendously printed, sorry. 0.1 seconds. By the time the car is at rest, so V is 0. Oh, I hate the order of this. Ooh. Anyway, for part A, calculate the deceleration of the car. So we've got enough, we can use A equals V minus U over T. V is 0, U is 20, time 0.1. That's going to get me, if I calculate that, minus 200 meters per second squared. That's the acceleration. This had asked for the deceleration. So that is 200 meters per second squared. Now, because that acceleration is so big, that's why if you crash into a wall, generally it's not good. If big deceleration is going to mean a big force. So for part B, I'll just work down the page actually. Calculate the force exerted by the wall on the car. For that, we're going to use F equals ma. Force is what we're trying to get. The mass is 1,000. And the acceleration or deceleration is 200. So we get 200,000 newtons. So that's why it hurts so much if you crash your car into a wall. Right, turn over to page 191 for me, please. We're going to spend a little bit of time looking at Newton's third law. So we've got Newton's first law and Newton's second law already. So Newton's first law, in the absence of unbalanced forces, an object will continue at rest, or if moving, will continue to move at a constant velocity. And Newton's second law, the acceleration of a body is inversely proportional to its mass, directly proportional to its force, and acts in the direction of the resultant force. So they just mean that if for Newton's first law, if the forces are balanced, it's going to just keep doing what it's doing. And the second one, if the forces aren't balanced, the object's going to accelerate. Newton's third law is that every action force has an equal and opposite reaction force. So that means that if I push you with a force of 50 newtons, I will feel 50 newtons pushing back on me. Now, quite often people will say, well, how is there ever a resultant force then? And if we think back to objects that we were calculating a resultant force on, so for example, this here, these aren't like equal and opposite forces. These forces here are acting on the same body. You'll hear me talk about Newton's third law forces. So every action force has an equal and opposite reaction. So I would call them like a third law pair. One of the rules for Newton's third law pairs is that they're always acting on different objects. So this is a thrust acting on this object, and these are resistive forces acting on these objects. So Newton's third law pairs are always the same type of force, and they are always acting on different objects. So they do exist in this, we just haven't included them in our diagram, because this here is what we would call a free body diagram. And anytime we're drawing diagrams like this to do our calculations, we only really involve the forces that are acting on the object that we're talking about. We haven't included the forces that are pushing down on the ground or pushing on the air. Okay, This is just like the air and the friction pushing on the object itself. So that can take a wee bit of a while to get your head around. I'm not sure if I have done a great job there. I will keep going though and keep trying. So every action force is an equal but opposite reaction force. So Newton's third law pairs, and they're always acting on the same object, and they're always the exact same type of force. So in other words, Newton noticed that forces always act in pairs. Two forces are always equal in size but opposite in direction. Now, there's a couple of examples that we need to draw on here. So, got my diagram of a guy starting to run who has the biggest hands in the world. And we're looking at what forces are acting whenever you start to run. So pause, get that drawn in, please. So, whenever you are like either starting to walk or starting to run, your feet push back on the earth. I am moving my feet here, you just can't see it. So your feet push back on the earth, and then like the earth pushes back on you. So they are the two forces. So I'm going to write them in here. So the force of your feet on the earth, so that, if in this situation, is going to be going that way. So this foot pushing back on the earth, okay? And because we're talking about Newton's third law pairs, the other one is going to be equal but opposite. So it's equal to the force of the earth on your feet. Now, there's one wee sneaky way that I always remember Newton's third law pairs. Once you get what one of the forces is, you just swap the order of the words around. So the force of your feet on the earth is equal to the force of the earth on your feet. You just swap the two objects around. So that backward force there is going to be equal to the forward force. Now, just to go back to what I was saying there and trying to show you with that wee diagram from the work from the last lesson. Whenever we would be drawing the free body diagram for this person, like the thrust force, that is the running force. It's this one here that we draw on. We draw on the force of the earth on your feet. We're only ever drawing on the forces acting on the object itself. We don't draw that one on. It still exists, but we just never include it in our diagrams because it's not going to impact the object, which in this case here would just be the person. So I want us to also make a wee note here of the effect that these things have. So the force of the earth on your feet is what actually moves you forward. Okay, and then the force of your feet on the earth, it actually moves the earth ever so slightly back, but this mass of the earth is massive, so you don't notice it. It's just like a tiny amount. If you compare the size of the force you're applying onto that big massive mass of the earth compared to the equal but opposite size of the force on you, where your mass is so much smaller, then obviously it's going to have much more impact on you. So this one moves the earth slightly backwards. Okay. Next example is a block of wood on a table. Now, this seems like such a simple, straightforward thing, but there's a bunch of forces acting here. But as I say, normally we don't bother marking them all on. So apologies if I cause confusion here, but sorry. So the first pair that we are going to be marking on our diagram is the contact force, like the physical pressing of the box on the table, and then the opposite of that is the table pushing up on the box. So the first pair is contact force of the block on the table. So think about, before I mark it on, the direction that is going to be. Block on table is going to be pushing down, is going to be equal to, and remember the wee trick, the contact force of, switch the words, the table on the block. And again, if you think it through logically, table pushing on the block, it's going to be pushing up the way. So we've got a downward force here and an upward force here. The pink ones I'm marking on here are the contact forces. Okay, now there's a second pair of forces acting here as well, and to make matters worse, all four forces that I'm marking on here all have the exact same value size. So that is, like, I can see where the confusion comes from. So the second pair of forces is going to be like basically the weight of the block. Now weight is a gravitational force, that's the type of force that it is. So it's the gravitational, oh, spelled that a bit dodgy, force or pull, maybe I should go for pull there, I'll change that, of the earth on the block. So the earth is pulling the block down the way, and that's going to be equal to, this is the one that is extra hard to get your head around, the gravitational pull of the block on the earth. And I'll talk a little bit about that in a wee second. So it's going to be pulling the earth upwards. So down the way and up the way, that's those two forces. Now, see this is quite cool. Absolutely everything with a mass has a gravitational pull. So right now, you, because you have a mass, have a gravitational pull around you. The bigger the mass, the bigger the gravitational pull. So if you think about the size of you compared to the size of the earth, it's so tiny that it's insignificant. Now, there's an episode of Family Guy which has a really good joke on this. If I taught you last year in physics, I did probably show you this. But basically the joke is that Peter gets so fat that small objects start to orbit around him. So it's just a joke that his mass has got so big that the gravitational pull is so big that things have started to orbit around it or around him. I love it whenever there's wee physics jokes in programs like that. Anyway, so yeah, normally like in the classroom, if we're all in it, I would always be saying, so right now, you are all attracting each other, because anything with a mass is going to attract anything else with a mass. That's the gravitational pull. But it's just that our masses are so small compared to the mass of the earth that we don't notice any of the effects of it. Quite cool, eh? Right, over the page to 192, we're going to look at friction here again. Not again, as well. So, definition of friction. I apologise, this really should be a much bigger deal in your notes. This is a definition that you need to know. So friction is a force that opposes motion. It's quite a funny wee force because like we only notice it once something starts to move. I suppose it only really acts once something starts to move. Because it's a force, it's measured in newtons. In general, the rougher a surface is, the more friction it'll have. This is all stuff that you will know already, but quite often the definition people don't know, so do make sure that you learn that. Friction between two moving surfaces can cause a lot of energy to be wasted as heat, and lubrication will cut down on this energy loss. So for example, putting oil in an engine, which I need to do in my car, or oiling the chain on a bike, or ball bearings would quite often be used in things to reduce the force of friction as well. Now, friction isn't always bad. It's useful. Like if there was no friction, we wouldn't be able to walk, because do you remember I was just talking about there, like with this, let me get it, like we push back on the earth and the earth pushes back on us. If there was no friction, that wouldn't happen. And you notice that whenever it's icy, that's the lack of friction that makes it hard for you to start walking, or I suppose stop walking. Obviously applying your brakes in a car, if there was no friction, they wouldn't work. It would just be a nightmare. But friction can also be a nuisance. So like air resistance or drag forces are all because of friction. Now, this is the stuff I've been going on about with the two sets of information in questions. So you may be asked to calculate a friction force like we have previously looked at using Newton's laws. Summarise how to do this below. Now, I was going to get you to try and do this yourself, but I'm a wee bit of a control freak, and because I know it is one of the areas that confuses people the most, it's the questions that people make wee mistakes in the most, I want to just use this as an opportunity to go back over it again. So I'm going to write this in, you need to copy down what I put in. So, if an object is travelling at a constant velocity, Newton's first law applies, the forces have to be balanced. So that means the friction force is going to be equal to the forward force, right? Now, this bit here is the bit that always catches people out. This friction force stays the same for the rest of the question, even if the forward force changes. Now, I have put in a wee disclaimer there, unless they tell you otherwise in the question, which I hope they don't, because that'll just throw a spanner in the works and just add extra confusion. So this, I'm going to make a wee list of the questions that we've done that are like this, just so that you can refer back to them and know what it's talking about. So it's like example 2, which is on page 181, which feels like forever ago that we did that. And also those questions that we looked at earlier on today. So question 6 and 8 on page 189. So those questions all used that fact of telling you that something was going at a steady speed when the forward force was such and such. And you use that to get what the resistive forces are. And then you keep that same friction or resistive forces for the rest of the question, even when the forward force was changed. Now, the other way, and actually probably the more common way that friction, well, not more common, I tell a lie. The other way that friction will appear in questions is in questions involving road safety. And do you know what? I think some of those end of topic questions that we did sort of cover the same thing. So for now, all I want you to do is have a read through page 193. I think I've gone on long enough. 1, I'm sick of the sound of my own voice. 2, I think this video is about half an hour, and if you've been pausing it to write it down, if we start to do this, it's going to be too long. So for now, just have a read through this, and I will do it next day. So that is me. I will see you next day. Bye.